Let me go ahead and get us started. I know that people will come trickling in as we get started, but I want to make sure there's enough time to cover the material. Just kind of give you the heads up. I think you know this, but it's good to remind you. Obviously, we have the lecture today, Monday, and then again on Wednesday. You'll have the MC this Friday, and you'll have the test next Monday. All right, so that's where we're headed. We're headed for the test. Now, Don wanted me to talk to you guys about the review. He was thinking Saturday, 1 o'clock. He likes to do it 2 days before. I know in the past it's been more on a Sunday, so he wanted me to kind of check with people, thinking if they, Sunday, not completely opposed to it, if that's the only time people could do it, if that worked best. But I don't know, does anybody have any strong feelings? I'm thinking Saturday made a whole lot of sense, so yeah. All right, so plan on that. I guess we'll write it on the board here, but 1 o'clock on Saturday, then plan on that, and I'll put it on the board on Wednesday so that everybody will. It says he prefers on Saturday. I'm sorry. Did I say that backwards?
Saturday's good.
Saturday's good. Only because that's the 2 days ahead. And 2 days ahead, whoops, excuse me. Two days ahead is usually pretty good, because then you can find out what you still have to work on here. So, but he wanted me to check with people.
Class on Friday.
When does the MC meet? 2 o'clock? 2 to 5?
2:05.
2 to 5, it's in PS 116. I take it by that you haven't been going or haven't been enrolled, and you're not enrolled? Technically you need to be enrolled into it, but at this point that's too late. But I'll just say just show up now. But that's why at the beginning of the semester I said, you want to sign up for this, it's well worth your time. But maybe I should ask you guys, for those of you who've been going, is it well worth your time? Yeah. So anyways, let those who are in Physics 102 know, because people don't realize it. And make sure you sign up for it next semester also, because the classes just get more advanced and you're going to appreciate that Friday afternoon more so than you do now. Okay, so I always encourage people. It's kind of what makes the difference in our program and not making it through our program. I mean, there's always going to be it makes a big difference, I guess, on those who really take advantage of it, those who need some help. I mean, there's going to always be those who it just comes natural, they have no problem with the class, and there's always going to be those who don't take the class serious and don't show up. But it's most of you who are in that middle ground there that can make a difference. It can make you difference of failing to passing, or from getting a C, getting a B, or from getting a B to getting an A. Anyway, so that's the progress this week. As you know, we finished chapter 11 on Wednesday when I saw you last. The last piece of it was on conservation of angular momentum, and so we finally got to the point of we've done all of Newton's 3 laws of motion, and we've done all the conservational principles. I had a chance to do one example for you, and that's where I want to pick up is more examples, and then hopefully get into chapter 12. Do want to emphasize no new physics in chapter 12. I like this breakdown of the tests and where we get into this third test, because all this hard stuff was at the beginning, and you've had a long time for it to sink in. Probably still hasn't completely sunk in, but you've got 7 days before the test. And I'll just say, the last bit of new physics was given to you on Wednesday, that conservation of angular momentum. And so there's 12 days between the end of that lecture and the test. And that's a long time. And a time you're going to need for you to practice these problems, for it to sink in, and just to realize no new physics. Now, don't get me wrong. There's some interesting stuff in chapter 12. It's not like there's nothing to do in chapter 12, but there is no physics. It's just an application of the stuff we've already learned in particularly these two first chapters, 9 and 10, which were pretty long. So 9 and 10 were pretty long. As you recall, 11 was pretty short. Best thing I think I can do is get out my calculator, get out my book, open it up, take a look. It looks like my notes said we did number 25 already. Let me jump then to number 37. Number 37 is another really good example one. It says this. It says a wooden block of mass capital M resting on a frictionless horizontal surface is attached to a rigid rod of length L and of negligible mass. Let me draw an aerial picture of that. He's got this big block which he calls mass M. It's connected to this rigid rod of length L. It doesn't really say how big the block of mass M is, and so by that, I think indirectly is implying, otherwise we couldn't do it, that L is much bigger than the width of this, so we can roughly say that all this mass M is at a distance L away. Yes, some is a little closer, yes, some is a little further, but without specifying what it is, we're going to probably just assume that it's all about L, maybe a little more, maybe a little less. I mean, of course, obviously, would have to be some kind of variation in there, but not too much of a variation. So it's kind of like that blob we did on number 25, that the blob is at the end of the meter stick. And of course, the blob does have size, but thinking of it as a point object. And so that's essentially what we have here. It says here that the rod is pivoted at the other end, and I probably should have kept reading it here, but what he means here, and I'll put a little X for the pivot point there, but that's the pivot point. In other words, this thing can spin, okay? And so it's sitting on a table, and it can spin. It says here a bullet of mass little m is traveling parallel and horizontal to the surface and perpendicular to the rod with a speed of v. It hits the block and becomes embedded in it. All right, so over here, I'll draw a bullet of mass little m traveling with a velocity of v, heading towards the block and going to hit it perpendicular. Okay? Collision. Gets embedded. Type of collision. Perfectly inelastic. So good, you're seeing this idea that this is really an angular problem, but how would you have done it if it was a linear or a translational problem? You would have said, hey, it's a collision. What do you know is conserved in the collision? You would have said momentum, right? Of course, that would have been linear momentum. So now we're going to look at angular momentum. You get the idea. Here's the question. A, what is the angular momentum of the bullet block system? And B, what fraction of the original kinetic energy is converted into an internal energy in this collision? All right, so we'll start with this whole idea here. Is linear momentum conserved? Is angular momentum conserved? Is energy conserved? Well, why don't we do this in the order that we learned them? Way back in Chapter 8, or 7 and 8 hooked together, we had this principle of conservation of energy. Is energy conserved? So somebody's saying no, somebody's saying yes. Hopefully you're all saying kind of the same thing. Is kinetic energy conserved? No. But is energy conserved? Yeah, so that was that idea of conservation of energy. We always have conservation of energy. There was no really ifs, ands, buts about it. Is energy conserved? Yes. I mean, you don't need to know anything more about it. You just know absolutely yes. Energy is conserved. No questions asked. Now, what might be a more detailed question is kinetic energy conserved? Well, that's the elastic collision. We don't have that here. We have a perfectly inelastic collision. So what we are saying then is something like this, that the original kinetic energy is going to become what? Well, you can imagine what might happen as this thing gets embedded. Can you see kind of that physical picture? What's going to happen next? Can you kind of see how it's just going to be then spinning along here? So there's going to be some rotation going on. So I would say that this original translational kinetic energy now becomes a rotational kinetic energy. Anything else? Yeah, oh, absolutely. All right, there's heat in there. That's why the whole idea of calling it a perfectly inelastic, or just that inelastic, means there's some heat created here. All right, so this would really be my first thoughts as I think about this. Is energy conserved? Yes. Is kinetic energy conserved? No, there is some heat created there. All right, so there's thought number one. Thought number two brings us into Chapter 9. Is linear momentum conserved? Well, this one, is linear momentum always conserved? No. What was the condition for linear momentum to be conserved? Right, no outside forces, nothing external to our system. So let's define our system here. Do you want your system to be what? Kind of makes sense. Maybe it should be the bullet, the block, and this lever arm or what, rod, I guess is what they call it. So there's my system. Are there any outside forces? Okay, you might say gravity, but let's say the impact is really short period of time. And from an aerial view, let's just say there wasn't a gravity. I mean, that's a good discussion to itself. But real quick, impulse, okay? Kind of like we did the problems with linear momentum. If we had some friction, could we still get away with conservation of linear momentum? And we could if we said immediately before and immediately after. And then as it slid, we'd say, okay, well, then momentum is lost. So I would say the same thing with gravity. Even though there's a gravity, if I could take the momentum right before impact and the momentum right after impact, and even then I would say gravity would be in this picture kind of a in and out of the board direction. So now I'm not even going to worry about gravity. That's not my main one. What else is going on here? Do you see it? Is there an external force? It's on a frictionless surface, so no, not friction. Anything else? Yeah, something's got to hold it at its pivot point. I mean, the only way this is going to work is, say we drive an L right here, put a bolt, right? I mean, what if this was not here? What if there wasn't a bolt? What would be different about this problem? Yeah, it would have hit it and it would have moved in this way, right? And then we would have said, yes, conservation of linear momentum. Then we would have said, no external forces. But the whole idea that by putting a bolt here, what ends up happening is when this hits, which would have normally have gone that way, this right here is applying a force F that way. That bolt, that hinge, it's applying a force. It's applying a force into the table. So is there some external force? Oh, absolutely. So is linear momentum conserved? No way. And I can't tell you how many times I see this on test number 3. 1 week from today. But it's not going to happen this semester because you're all being warned here right now, right? You're not going to apply conservation of linear momentum to this problem. It's not valid. You wouldn't even think about it because there's an external force here, right? And so don't even go down this road. It makes no sense. We've got an external force. If we didn't, it would be a very different problem. It wouldn't spin, it would translate. And then we could use that. Yeah. But that's not what we have here. So we do have force. So keep that in mind. That's really one of many reasons, but a main reason of why I picked this one. It illustrates it very, very well here. What is going on with our 3 conservational principles? That's the big lesson here. I'll say it again. What are we trying to get accomplished this semester? Mechanics. Newton's 3 laws of motion. 3 conservational principles. You know those. You can give me any motion. You can explain anything that goes on in this universe. Okay? Those are our mechanics. Any mechanical thing, I guess I should say. And I suppose I should say any non-relativistic mechanical thing here. Okay? And then finally we get to the one relevant for this chapter is angular momentum conserved. Well, is it always conserved? No, just like linear momentum. What was the condition here? No outside torques, right? All right, so do we have any outside torques? We clearly have a force, but do we have a torque? Okay, good. But before we even go that far, don't we have to say a torque around what axis? Right? Isn't the moment of inertia? Isn't the torque, isn't the angular momentum all calculated relative to some axis? Wasn't that the point of Wednesday's lecture? Especially when something is going in a straight line like that bullet. Does that bullet have angular momentum? Answer? Depends what axis we're talking about, right? Could be positive, could be negative, could be 0. So we went through a long process to show you that the angular momentum was highly dependent on what axis you're talking about. And I would say the same thing here with this torque. What axis are we talking about? And I think it makes only sense that we would be talking about the one it's eventually going to be spinning around. The one it's eventually going to be spinning around is right here. And so if you pick that as your calculation point, which I think you should, I mean, why else would you do anything other than that? Although it might be nice with more advanced problems here later in this chapter or in the next chapter, say, well, what about calculating it around a different axis? But for now, let's pick the obvious choice. The obvious choice is, let's pick this as the axis. And if I do that, I heard somebody say, how much torque do you get? Well, since torque is R cross F, and the force is right there at the axis, the R is 0. So, do you have a force? Yes. And hence we don't have conservation of linear momentum. But do we have a torque? No. So do we have conservation of linear momentum? Yes. And so there are our two principles that we are going to use. Conservation of energy, conservation of angular momentum, but not conservation of linear momentum. In fact, if you tried to solve this, you would see that if you tried to do it this way compared to this way, you're going to get a different answer. Actually, I don't think you will for this one. Next one you will. This one they've overly simplified by not giving this thing size. But on the next one we'll give it size and it'll make a difference. So I think if we had done this one, I think we might get lucky. But I don't want to go down that road. I don't want to even see if I would get lucky. I just want to see. I need to ask that question. What principles, what fundamental principles I can use here? And so again, especially getting into the third test, and more so as you get into the final exam. I think the questions, just answering them gets harder, because the first thing you have to ask yourself is, what kind of problem is this? You know, what kind of principles am I going to use to solve this? Do I do Newton's laws? Do I use conservation of energy? Do I use conservation of linear momentum? Do I use conservation of angular momentum? And so we've been exposed to all of those. And the list just grows. If we get to the final exam, there's going to be Newton's universal law of gravity thrown into the mix, plus there's going to be an Archimedes principle and a Bernoulli's principle as we get into our fluids. And so you'd have to stop and ask yourself what principle it is. And that's what I'm doing here. I'm stopping and asking myself, what kind of problem is this? It's mechanics. How am I going to approach it? And in this case, I'm using two of the three conservational principles here. And so that seems to be the approach there. All right, so now that I've answered those, I begin to do this, because this one is why they even asked. I mean, look back here at A. It says, what is the angular momentum of the block bullet system? And I got to admit, when I first read it, I was a little disappointed. They don't say. Do they want it before the collision or after the collision? Well, how come they don't say? Yeah, we could argue it's the same, right? They don't specify what it is purposely, because you can do it before, you can do it after. Your choice. You're going to get the same number. All right, so which one's going to be easier, I suppose? So we do it before the collision? We did a lot of those already back on Wednesday. So why don't we do it before? So we'll solve it for the initial. So over here, I'll put A. All right, so A is, let me get the initial angular momentum. And so the initial angular momentum is this bullet before the collision. And since the other object, this block, is not moving in any way, I can say that the total angular momentum of the system is all in the bullet. There is none from the block before the collision. And so if I kind of draw a line out here, this is then R. The mv is the linear momentum, and that is the angle, or the supplement of the angle, between R and P. And so it looks something like this. It's R, P, sine phi, where P is mv. And I'll even make one more step. If you see it there in the geometry, what is R times sine phi? Well, got a nice little triangle formed here. This happens to be the hypotenuse of that triangle. Sine phi happens to be this side of length L. So doesn't hypotenuse multiplied by the sine of phi give me length L? So, sure enough, MVL then is the answer they're looking for. Now I suppose I need to put a direction here, since this really is a vector. And I've got two options as we went through, and try it again. Number one is, and you know, what happens if it actually hits and then starts spinning. Maybe that's the easiest way to see it, although that's technically after the collision. So maybe that's not so easy to see, but I'll do both. I'll do after the collision for a moment, because after the collision, I see that hitting and spinning in a clockwise direction. And if I take my right hand and curl my fingers in a clockwise direction, I get into the board. So I'm thinking that that is a negative k hat direction. That is the angular momentum. On the other hand, if we want to use our other definition here of the cross product, we can take our right hand and we can say, all right, put your thumb here in the direction of R. You can put your fingers then in the direction of P, and my thumb should give me the direction. A little subtlety here that I didn't realize while I was saying it on Wednesday, but if we do this, make sure that we position our hands this way, and let's see, not, maybe there is not a knot, on some of this, and somebody was showing me after class, there was two ways to position, and I go, oh, you're right, I should have said this. I should have said, oh yeah, you position it, but don't forget that you want to set it up so that you can move one into the other. So that kind of helps you which way your palm is. So you cross it this way, whereas if you set it up something like this, you can't move your finger around that way here. So set it up so that you are closing, you know, and that's kind of the cross thing. So you got one in this direction, one in the other one, and then you close them together. I kind of like to do just fingers in the first one, close to the second one, and then my thumb, and so I'm not starting off this way. But whatever works better for you. I know your author does this one, and when I was a student I learned it this way. Put your fingers in the direction of the first, close them towards the second, and your thumb will give you the cross product. But either way you want to do it, hopefully you can say, I mean, your fingers in the first one, close it towards the second one, thumb is into the board. So either way you want to hold your right hand, or either way you want to look at the angular momentum before the collision or after the collision, they all agree with each other that it's going to be into the board here. And so that's the point of this problem, is to calculate the angular momentum and realizing it's the same as before and after. And even though the angular momentum is, the linear momentum or translational momentum is not. And that's really what I wanted to emphasize. I also wanted you to see the same thing I said on Wednesday, that could you have something going in a straight line and yet it still have angular momentum? Yes. And this is a good example of that. And you got a good homework one too on that with it's got a little flagpole, and well, I'll let you read the flagpole, and the little object on the end of the flagpole, the little ball comes off and falls, and you know, when it falls down in a straight line. Does it have angular momentum? Well, yes or no, depending on what your origin is, what your axis is here. Okay. And so in our case, ours does have some angular momentum. It happens to have a negative amount. The real crutch of the problem is then B, what fraction of the original kinetic energy is converted into heat? Right there. So here's the second part of the problem. What is Q? Well, actually, I don't think they quite asked for Q. Let me read it again. I think they've said, yeah, what fraction of the original kinetic energy is converted into heat? So what they're really saying here is not how much Q do you have, but how much Q compared to what you started with. And maybe that's a tough spot right there. I mean, even understanding the question, what are they asking for? They're not really asking for Q. Turns out we wouldn't be able to solve Q without having to have some numbers to punch in here. But we can solve for the fraction, and that's what they're saying. How much have you created? How much internal energy compared to what you started with? What fraction of the original? So this is the original, and this is how much heat. So that divided by that. And hopefully it's less than 1, right? It's got to be conservation of energy. We know that that number has got to be smaller than that number. These two together got to add up to that number here. So what fraction? So now we can go through a little bit of math here. In place of Q, I guess I would put 1/2 mv squared minus 1/2 I omega squared all over 1/2 mv squared. So that's really what they're asking. And if I simplify this a little bit, you can see that this first step is 1, and this next step here, the 1/2s cancel off, and you end up with I omega squared over mv squared. Now if we come back to a statement we made earlier here, that the original angular momentum, which we just calculated as mvl in part A, is equal to the angular momentum after the collision. And if I was calculating the angular momentum after the collision, I'd say, well, look at this thing. It's got a rotational inertia, a moment of inertia, and it's got an angular speed. So this is how I would calculate it after the collision. This is how I just calculated it before the collision. Now, the reason I say all that is because you're probably noticing that there's an omega and a v connected together, and sure enough, this is how they're connected together. So if I write this as an omega over a v, then this becomes an ml over I. And that then becomes useful here, as I say that this is then 1 minus, and I've got an I over an m. I'll leave that alone. But then I have an omega over v, which is ml over I, and it's squared. And so now I can begin to start canceling things. So here's a 1 minus, and let's see, the L squared is going to remain alone. But one of those m's with 2 of those leave 1 upstairs. And 2 i's down here with 1 upstairs leave 1 down there. And so that's what I have so far. And I claim that can be simplified a little bit because this I involves a calculation about the moment of inertia. Well, this comes back to our beginning part then. What would be the I for this configuration? And they've given us the kind of the easy one to do, where we can just add up a bunch of point masses, a bunch of chunks. And so we're going to add up the chunks. In this case, there's 2 of them. There is the bullet, which is probably a distance of L squared, and then there is a block, which is a distance from L squared. So we've got the 2 pieces that we are adding together to get the moment of inertia. And that's why this problem is going to be easier than, say, the next one. The moment of inertia is then just, 2 chunks of mass, not giving size to them. So I can put that into here. So this becomes then an ml squared plus capital ML squared, which again, that can be simplified because as you can see, there's an L squared in the bottom that can be factored out, canceling with an L squared in the top. And so now you've got something that looks like this. And so finally I can finish the problem by getting a common denominator of little m plus big M. And then over here would be little m plus big M minus little m. And so we get capital M over little m plus big M. Ta-da! Okay, and so using my principles here, which may be more complicated principles, I can come up with the answer to B. What is the fractional law? So it depends on this ratio of the masses. Hopefully not a surprise to you. Didn't we do that? Of course, we did it with a linear one. But wasn't that the whole idea of a lab? Not last week's lab. I think it was the week before, our ballistic pendulum. We shot that little ball, that little spring-loaded cannon. And you were supposed to measure the momentum and the energies. And when it was all said and done, you took the ratio of the energy that was produced because of the heat, or technically the internal energy, divided by the initial kinetic energy. Do you remember that lab? And you did it. And then you calculated the ratio of the masses, and you noticed they were pretty close to the same within the experimental era. That was the point of that lab. And so we see that here. I think we did some linear problems like that too. But we see the same thing here with the rotation. Well, hopefully if that one made sense, the next one will make sense. It's really kind of the same one, but worth doing again because I just think it takes a little while to sink in. It's number 50 in your book if you're got your book there and following along here with the problem. But it's very similar to this, except now we don't just have some point masses. This one says, in 50, it says a projectile of mass little m moves to the right with a speed of little v. The projectile strikes and sticks to the end of a stationary rod of mass capital M and of length d, pivoted about a frictionless axis through its center. So that description is something like this. This then is this rod of length d. It can pivot around a frictionless axis at its center. A mass of capital M, of little m and velocity v are being shot at the rod. The rod has a mass of capital M, if I read this right. So projectile of mass little m moving to the right with speed little v. The projectile strikes and sticks to the end of the stationary rod of mass capital M and length d, pivoted around a frictionless axis through its center. So there's the problem. A, find the angular speed of the system right after the collision. B, determine the fractional loss of mechanical energy in this collision. Okay? And so it's really kind of the same questions, although this one asks for angular speed instead of angular momentum. But it's the same basic idea that, again, we should probably start off. Does the initial linear momentum equal the final angular momentum? Linear momentum. Does the initial angular momentum equal the final angular momentum? And the third question, does the energy before the collision equal the energy after, after the collision? Yeah.
Like the instant when it hits, it hasn't really turned at all, so why would the linear momentum not be conserved? Like at the very instant, like it hits the thing on the pivot, and it hasn't really turned at all, wouldn't it still be? Has
it hit it?
Yeah.
So has a force?
Yeah.
Okay, so then I would say there's a force down on the axis too.
Okay.
Now you might say it hasn't moved yet. That's fine. But that impulse does transfer, it's kind of this unrealistic instantaneous. But if you're going to give me an unrealistic instantaneous force here, then I got to give you an unrealistic instantaneous force there. And so it has set the pattern for the rotation, even though it hasn't started its movement yet. So it's like saying it has velocity but hasn't moved yet, Yeah. All right, so let's run through these three again. It's again the same one I wanted to do, 50, because I wanted to go through these steps. And I thought if I did it twice, you would be set and pretty for doing the homework. You'll go home tonight, you'll pan out the homework in a couple minutes and say, oh, there's going to be an easy test. Nothing could be better than that. So, but you may not. So just in case you don't, I do want to encourage you. You need to try these, okay? If you struggle with these at all. And a lot of people have in the past. So hopefully you guys won't, but a lot of people have in the past. There's 7 days away to the test, so I want to give you a lot of time. That's why those 12 days we're talking about. And those 12 days have now become 7 days. And next time I see you on Wednesday, it'll become 5 days. And then Don will see you on Friday, and it'll become 3 days. And Don will see you on Saturday, it'll become 2 days. And so eventually that test will get there. But you want to try these, just kind of plan your week ahead to see how much effort you need to put in. Do I need to study 1 hour, 2 hours, 20 hours, 40 hours? How much study time do you need to put? Well, again, let's go through these. Same as before here. This is our chapter 8. Is energy conserved? That should be the easiest question. Answer? Yes. Hand down? Yes. There's no ifs, ands, buts about it. There's no, well, what if this? No. Energy is conserved. Now, you may have gained energy from the outsource. And it may change forms, I realize, and it may convert into heat. But we do know this, that the energy is conserved. So I can write this then as the problem before, 1/2 mv squared, which is the initial kinetic energy, is then going to become a rotational kinetic energy and some heat on that impact. And so as these molecules interact, as this object strikes, the molecules are hitting each other, pushing on each other, and what ends up happening is the molecules are now moving faster because of that. And that's the heat that is formed in that impact. So this one is true. No real question about it. The tougher one to ask is right here. Are both true? Are just one of them true? Are neither of them true? Because here, to have linear momentum conserved, you have to have no external forces, no outside forces. And so I claim that if there weren't any external forces, in fact, maybe I should ask you guys, what if there were no external forces? What would this problem look like? Yeah, so like the other one, where does the external force come from? Yeah, it comes right here. It's that hinge. So during this impact, as this puts a force this way, this puts an equal amount of force. So the net force always comes out to be 0, and that's why we don't, have a linear momentum here, right? That's why we lose a linear momentum. It had a linear momentum here, then this force outside of our system took it away, okay? Or to put another way, just looking at the rod, this has a force that way, this has a force that way, net force on the rod is 0. So the rod never gains any linear momentum. It does, though, gain a rotational momentum. More on that in just a second. But I should ask you this, because you have a homework problem, and I want to give you a hint on it, because this one is always giving students a hard time. It's number 36. And when I'm done with this one, let me give you a little hint, but this is the first leading up to number 36. I want you to think about, what if that hinge or that bolt or that nail, what if this axis was not here? What would be different? Well, good. I hear both. I mean, from a mathematical point of view, if that wasn't there, then there would be no external force, and then we would have conservation of linear momentum. Physically, as you guys were saying over there, is, well, what would happen in this picture? What would happen when this, say this is a ball of clay, hits this rod? If this was just no pivot point here, if this was just floating in outer space, what would happen? It would hit it, and what would it do? Yeah, it would be moving through space kind of like this, right? And so it would have a translational momentum as well as a rotational momentum. And that's why we would have, that's how we would be conserving both of them. We would have the original linear momentum conserved as well as the angular momentum conserved as it was flying through space. But with this extra hinge there put right there, or with this axis placed right there, what happens instead, you have an external force. You don't have a linear momentum, and it just has the angular momentum. And so with that hinge, it hits and it just spins. And so that hinge makes a big difference. It makes a big difference mathematically. It makes a big difference in the physical result at the end. And all of it is because of that added force from that hinge. And that's why I picked these first two problems. And that's why I want to give you more of a hint for number 36 here. But I'll wait till the end of this problem. Okay, so you answered hopefully the obvious one, that does the initial linear momentum equal the final? No, because we have an external force. But with that said, just like the last one, do we have conservation of angular momentum? Well, yes we can, if we have no torque. How could we get no torque? If you calculate everything from this axis, torque being R cross F means that any forces that are acting on that hinge would give you a 0 torque. There's no distance involved. And 0 torque means that the angular momentum before does equal the angular momentum after. So yes, we do have conservation of angular momentum. So a lot like the last problem. Yes, we have conservation of angular momentum. Yes, we have conservation of energy. No, we don't have conservation of linear momentum. We have a different scenario, if you will. All right, so once we know that, let's go back to the question A. It says, find the angular speed of the system right after the collision. Okay, well, let me do the conservation of angular momentum here. How about we think about the angular momentum before the collision? Well, just like before, if I draw a little line out here, this is R, this is then mv, and this is the angle phi. My first step for calculating angular momentum would have been R cross P, which would have come out to be R mv sine phi, which if I put R together with sine phi, I get d over 2. And so this is the triangle that is formed here between R, the hypotenuse, sine of the angle, gives me that distance, which is half the length of the rod. And so the rod is the length of d, half of it is then d over 2. So again, same thing we just saw a few moments ago. This is then the angular momentum before the collision. Now, what is it after the collision? Well, after the collision, I guess it would be I omega, right? And so maybe I'll put it down here, I omega. So I can carry this equation over here to this side of the board. Because that really is the question here. It says find the angular speed after the collision. So the angular speed omega then becomes this mv d over 2 divided by I. And so that's my conservation of angular momentum. Now, there's still more work to be done, but the rest of this goes back to previous chapters, which makes a nice review as we're getting ready for the test here. But this is what this chapter is about, conservation of angular momentum. Yes, it's true here. Yes, it gave me the angular speed. So, with a little bit of arithmetic here, I will write it as mvd over 2I. And then my I becomes the first object and then the second object. I've got two objects to work with. The first object by this point is that we have this blob of mass m stuck at the end of the stick. And so that's just going to be an m, and the distance away is d over 2 squared. And so that's just your standard, what is the moment of inertia of a blob? And so it's just the mi/ri squared. So there's my first piece. I got a blob, a distance d over 2. The second piece then is what is it of a rod about its center. Now we've done that many times, so let me not recalculate it, although you may not have committed it to memory quite yet here. But does anyone remember the rod center? Yeah, that's 1/12. So this should be 1/12 mass of rod, which they're labeling as capital M, and length of rod, which they are labeling as d squared. So there would be the moment of inertia of that one. Okay. By the way, I often get this question. Let me just ask it now. Do I have to have those memorized for the test? Well, something like this, I'd actually give it to you. Because the point of the problem is not trying to remember what is the moment of inertia of a rod. The point of this process is getting you to distinguish between conservation of linear momentum and conservation of angular momentum. Do you need I to solve the problem? Yes. So on the first page of the test, I will list, like that table has, what is the moment of inertia of a rod about its center, what is the moment of inertia of a disk, what is the moment of inertia of a sphere. So I'll put all those on the front page. The only thing that may come into the calculation is there may be a problem that explicitly says, calculate the moment of inertia of a disk about its center. Okay? And so if the problem says that, obviously, you need to calculate it. All right? So these problems can be kind of long, I know. And so I just want you to know that if the point of the problem is not calculate the moment of inertia, if the point of the problem is something else, and you need to use the moments of inertia along in the problem, I will list those and you can just look them up. Okay? So otherwise it would be a very long problem where you got to do the problem and then you got to go off to the side and calculate the moment of inertia. And there's just not enough time in a 2-hour test for that. So that's the idea. So something like this, I wouldn't expect you to go off and to the side and calculate it, and I would give it to you so you can go look it up. Okay? All right, so I'll keep going. I've got a little more algebra here to do. And let's see if I can simplify this a little bit. I've got the mv over d, and it looks like I can factor out a d squared. I don't know if that's helpful or not. Kind of looks like it might be. If I do that, I get an m over 4 here, and I get a capital M over 12 here. Well, that's kind of nice because this has a common denominator of 12, which would then be multiplied by 3. So 3m plus 12. And so if I write this as an mv, and I'll cancel off one of the d's. So there's my mv. I've got a 2d left over on the outside. And so this I'll write as a 3m plus a capital M, and then put the 12 upstairs. Remember, a compound fraction you can flip and multiply. So this 12 is really upstairs, which then means that 2 cancels with that 6. I mean, with that 2 with that 12, leaving a 6. So I have 6mv over d times 3m plus capital M. And so I guess that would be the answer to part A. What is the angular velocity of your system? And so notice that the final answer here is listed in the variables that were given in the problem. Things like little m, little v, little d. Notice I didn't leave it as I. And I think that's sometimes tough to kind of go, well, what does the author want me to do? Could I have just left it here? Well, probably not, because this says in terms of I, and I wasn't given in the problem. And so the general answer is, you know, where do you stop? And the answer is you need to give an answer in terms of the variables that were given in the problem. That's why I needed to convert I into the m's and the d's that make it up, and then simplify it from there. Okay? But there would be the answer to part A, what is the angular speed? Which then gets me to the real crutch of the problem. A just kind of helped me out along the way. But it is this question then, what is my fractional loss of mechanical energy? So it's the same question as before. What is my Q compared to the start of my energy? So the start of my energy is the 1/2 mv squared. Q then is how much heat is created. So again, wanted to make sure I did this problem like the last one, just because they think sometimes it's like, well, what are they really asking for? So they're not asking for Q, but they're asking for the fraction. What fraction compared to the original? What heat compared to the original, I guess I should say. So when I do that, then I can put, like we did in the previous problems, my Q, which would be the 1/2 mv squared minus 1/2 I omega squared all over 1/2 mv squared. Which, like we saw in the last problem, this first term becomes a 1. The 1/2s cancel off, and you've got an I omega squared and an mv squared. Now, again, we can begin to write this, and that's kind of the nice thing about that step there, is we've got the omega. So I can write this as 1 minus, and I guess I have an mv squared. I have the I, and then I can do my omega and square it. So when I square it, I guess I get a 6mv squared in the numerator, and a well, I'll just write the d squared first. D squared, and then I get the little m plus big M squared. And I guess there's a few things I can simplify depending on what I want to do first. I guess I will leave the I alone for a moment. But that's a 36 when I square it. One of these m's will cancel with one of the m's downstairs, so there's only going to be one left over. The two v's are going to cancel off, okay. Then downstairs I've got a d squared, and I've got the 3m plus capital M squared still to mess with. And that's where we can come back and do our I again. Our I was right here. And so I'll write this as 1 minus, and I'll put the 36m first. I'll put the d squared 3m plus capital M squared there. But now I can put in this I that we worked out earlier. And so this would be an m d squared over 4 plus a capital M d squared over 12. So more arithmetic to simplify here. I hope you see a d squared in each term that can be factored out and cancel off with that d squared. So there's my 36m here. But again, I'm hoping you see a common denominator of 1/12. So I'll factor out a 1/12 because that's going to make then a 3m plus a capital M left over here. Downstairs has a 3m plus a capital M squared, so that one of those downstairs can cancel with one of those upstairs. And for that matter, this 12 can go with the 36 3 times. So I get 1 minus, looks like I've got a 3m in the numerator and a 3m plus a capital M. And then finally, I can get a common denominator of the whole thing, 3m plus capital M, which would be 3 little m plus capital M minus 3m, which means then I get a capital M over 3m plus a capital M. Ta-da! Whew, wasn't that easy? Okay. All right, I'm joking you maybe with the easy part, but do you see the fundamental principle? I mean, the fundamental principle started out conservation of energy, conservation of angular momentum. Just put in the details, work it out, and boom, you're done. Okay, maybe 20 minutes later or 2 hours later, but we've just got to put in the details, go through the math, and sure enough, we will get the final answer here. Okay. Which then brings me to number 36. Here's a problem you're going to do. And in number 36, you've got a slightly different problem. It's a lot like these. Except there's 2 tricky points I want you to see here. So let me help set you up. What it has is 2 disks. They don't really say what kind of disks they are. I guess in my mind I kind of think of them as those shuffleboard disks or something. But that's not fair because they say they're different sizes. They give you the sizes. Look at number 36 here. It says here that a puck of mass 80 grams and radius 4 centimeters glides across an air table at a speed of 1.5 meters per second as shown in the figure. It then makes a glancing collision with a second puck that has radius of 6 centimeters and mass 120 and initially at rest. So this guy is moving, V. Has a radius of only 4, where this one is stationary, which has radius of 6. It's set up so it's a glancing blow. That is, the tip or the rim of the first one is just going to sideswipe the tip or the rim of the other disc. Okay? What do you think will happen next? Well, it goes on to say that the edges of the rim it says are coated with an instant acting glue. I like Velcro. All right, it's got Velcro there on the edges. And so what's going to happen is they're going to stick together. And then what? Yeah, and hopefully you're seeing here that what will happen is that when they stick together, they are going to be not only continuing in a translational effect, but that they are going to continue and have a rotation effect. And for the first little hint I want to give you is, are there any external forces here? In other words, is linear momentum conserved in this problem? Yes. Is angular momentum conserved? Yes. Is total energy conserved? Yes. So it's a little different than the two examples I just gave you. I had two of the three, but you've got all three of them conserved. It's supposed to make the problem easier, but I'm not sure it does, because, you know, it's like, hey, we've got all these options. And so this is the one I was saying about a few moments ago when we started that problem. You know, we just got done with 50. I would say, well, what happens if it didn't have a hinge placed in there? Okay? Well, when they hit, not only would it rotate, but it would also translate. So you'll have all three of those equations. That's why I said it's supposed to make it easier. With all those options, you got plenty of different patterns you can have. But linear momentum is conserved, angular momentum is conserved, and energy is conserved. And so that's warning number one, or hint number one. Warning or hint number two is, where does it spin around? Its center of mass. Is that where its contact point is? No. And for whatever reason, students will go on and pick it as if it's spinning around its contact point and do all their calculations from that point. And of course, you're going to get the wrong answer. That's not physically what happens. Okay, and so you can do all the math right you want, but if you don't have a good physical picture and understanding of the mechanics, you're not going to set it up right, and you're not going to get the right answer. It spins around its center of mass. That was the whole idea of the center of mass. Because wouldn't it be saying, what would you say about the center of mass? Once this thing is moving, if there's no external forces, wasn't that the whole point of the center of mass from chapter 9? Is to say that once we give our object size, we can take this object and shrink it down to some point, and that one point would act as if all the forces were acting on it. And in this case, once the collision has taken place and it's moving, there are no forces. So that one point should act like what? A straight line. It should be moving in a straight line. We know from Newton's first law that would happen, right? An object with no forces continues to move in a straight line. So apply that whole idea of chapter 9 to this. That continue this to move in a straight line. So here's what's going to happen. The center of mass will be somewhere about here. You need to find it, which is what makes it, I think, a tough problem. You need to remember that. You need to go back to chapter 9 and how do you find the center of mass? You need to realize it's not spinning around its contact point. And so there is the angular speed. What is the angular speed? And warning 2b goes hand in hand with this. If you realize it is spinning around its center of mass, so you need to find its center of mass. And so if you're going to calculate the angular momentum after the collision around its center of mass, where should you calculate the angular momentum before the collision? Around its center of mass. And it's too easy, especially looking at this before the collision, to say, I'm going to calculate the angular momentum around the contact point. No! Don't do that to yourself. Why would you calculate it around one point, only later to calculate it around another point? How can you say those two are equal? They couldn't be. You have to be consistent. If you're going to calculate it around one point, make sure you do it around the other point. And so that's the same really warning here, is you need to realize it's spinning around its center of mass. And not only is it spinning around its center of mass, then you're probably going to calculate its angular momentum around its center of mass after the collision. And if you're going to do that, then you better calculate its angular momentum around its center of mass before they have the collision. Okay? So don't do yourself in by calculating the angular momentum around different points and then say, oh, I'm going to use conservation of angular momentum. That's not going to hold. It's got to be calculated around the same origin, the same point. Otherwise, you don't have conservation of angular momentum. Okay? And so those are the three tricky little steps there. Now, with that said, hopefully then it'll be an easy problem for you. But even then, I think it still will be a nice educational problem. Well, how about we try another one? Enough of the easy ones, right? Let's go to 56. And actually 56, 58, 59, we'll do these three and then we'll go into the next chapter. But some of my favorite problems in the book are right here. They're really going to, well, maybe I shouldn't say the book because I like E&M more than anything else. But at least my favorite ones when it comes to mechanics. I mean, we've really got into some advanced stuff now. I mean, and you could really do some tough problems. And for most of you, it's problems that you've never seen before. A lot of you have seen the mechanics at one level of another from your high school or your Physics 102 or some other physics or science class. But seldom when we get to this point have students been dealing with rotational inertia, calculus, and so everybody's hit the wall, if you will. Everybody's hit something new here, and everybody's kind of on an equal footing. Maybe not, but chances are you've got it here. And here's a really good one. It's number 56. And it says this. It says, a solid cube of wood of sides 2A and of mass capital M is resting on a horizontal surface. The cube is constrained to rotate around a fixed axis AB as shown in the figure. Well, maybe I'll draw the figure. Here's the cube that they show. They show the front of the cube right here. And they've got it kind of going back in a three-dimensional view into the paper or into the view of it. And so here's the cube. And they've labeled the cube A, B, C, and D on this face. And if my three-dimensional picture makes any sense, I hope it does. It's sometimes hard to draw in 3 dimensions here on a flat board. But I'll call this face the front face, the one facing us. But this one labeled A, B, C, and D is the right face. And that's an important one. It's the right and left face that are going to become real important. So the face A, B, C, D, and the one opposite of A, B, C, D here, what I'll call the left face. Okay? Now, remember, they did say that the cube has dimensions of 2A. So 2A by 2A by 2A. All right, let me read it again. A solid cube of sides 2A and of mass capital M, so I'll put a capital M down here, okay, is resting on a horizontal surface. The cube is constrained to rotate around a fixed axis AB. So in other words, what they're saying here is this little point AB, or that line AB, is constrained to rotate right here. Or maybe the design is something like this. Somebody put a hinge here, kind of like you would do with a door, right? And so it can rotate, okay? And so just like this door can open, this cube, maybe I should have thought about bringing a cube, but I want to make sure you see this step. This is that step one. Got a good physical picture of what's happening. And I know this isn't quite a cube, but what they're saying here is this is the hinge, AB. It can rotate on that hinge. But since it's bolted in, it can't slide. But it can certainly then rotate. Okay? All right. So the cube is constrained to rotate around a fixed axis AB. A bullet of mass little m and speed v is shot at the face opposite of A, B, C, D at a height of 4/3 A. Okay, so over here, there's a bullet. maybe right about here. The bullet has a mass of little m. It's traveling with a velocity v, and it is about to hit and get embedded in the block at a height of 4/3 a. So more than halfway up. A is halfway up. 4/3 is more than halfway up. 2a is over the top. So this hits the block. It doesn't go over the top of the block, but it doesn't go under its center of mass. It actually hits it above its center of mass, the center of the block. And that's the important part of this. It says the bullet then becomes embedded in the cube. Here's the question. Find the minimum speed of the bullet needed to tip the block so that it falls over on the face A, B, C, D. Go ahead and assume that the mass of the bullet is much less than the mass of the block. Okay? So they're probably going to have something in there about it. They probably want us to realize that even though the bullet gets embedded, the block still has a mass of capital M. Okay, so we don't have to worry about the mass of the block increasing by a little value of m. It's just capital M still. So the mass before the collision is capital M. The mass after the collision is still capital M. So I'm sure that's why that last phrase is there. So I better pause here. Got a good physical picture of the problem now? Do you see what's going on? Here's the idea. Shoot the bullet at the block. I mean, think about what's going to happen here. What if the bullet is going kind of slow? What's going to happen? Yeah, I guess if it's going real slow, you probably won't see much of anything. But a little faster than that, wouldn't you kind of see the block kind of lift up a little bit and then land back down? And then the faster speed would make it go a little bit higher, right? But eventually, a high enough speed would do what? And does it have to be going all the way over? You have to give it enough speed so it does what? It gets up to the top, and then gravity can take it the rest of the way, right? So that's really the key to the problem. I mean, how fast do we have to shoot this so that the bullet, when it gets in bed, is going to make it go up to here? And then gravity will take it the rest of the way. We don't have to go faster than that, although that would work. But it says, what's the minimum speed? And so that's what we're looking for. We're looking for just enough speed that's going to make it arch up to here. And whoops, arch up to here, and then fall due to gravity the other way, right? All right. So let me ask the same questions I've been asking in all these collision problems. Is the initial linear momentum equal to the final linear momentum? No? You guys got that one? Good. No, why not? There's an external force coming from where? Yeah, that hinge, that bolt. I mean, this would be a different problem, wouldn't it, if you didn't have any external forces? I mean, if that hinge wasn't there, and I should even say if the table wasn't there, because this is sitting on a horizontal surface, but if this cube was just floating in outer space, what would happen when this bullet hit it? Yeah, we're back to this problem, right? It would hit it, and not only would it be translating, but it would rotating, and so the cube would be moving through space something like this. Okay? If you have the table on here without the hinge, then it would be even kind of interesting. You would hit it, the table would put a force on it, making a torque, and so it wouldn't rotate. It would just translate, a frictionless table. And so there we would have conservation of linear momentum, but not conservation of angular momentum. And we haven't seen any quite like that yet. Then, of course, what we have is a little different than all that together. We have the hinge. So the hinge puts a force back, so we don't have conservation of linear momentum. But it allows it then to tilt, and so then we have a conservation of angular momentum, but only if we calculate the angular momentum about what point? Doesn't it have to be around this pivot point? We can't do it around the center of the block, right? Got to do it around that point. Why? Because to conserve angular momentum, we have to have a torque of 0. And the only way you're going to get a torque of 0 is if the r is 0. And that only occurs when you calculate it around that rotational point. So just like I did in the previous two examples, I needed to calculate it around the pivot point. That's how I got a 0 torque. So same thing here, but a little bit harder. It's more three-dimensional here, but the same idea. So good answer to both of those. That is the linear momentum conserved? No. But is the angular momentum? Yes, as long as we calculate it around that point. And then finally, is the initial energy equal to the final energy? Oh, yes, absolutely. I don't know if that's even needed for this problem. This is a very different problem than the other ones. It doesn't say what is the fractional lost in heat. Oh, maybe it does later on. No, it just says what is the minimum value V required to tip it over. All right, so I'm not even sure I'm going to need this, but it's worth discussing. Let's go with the conservation of angular momentum. So conservation of angular momentum is true here. Okay, so I've got that. And now what I'm going to do is then go ahead and look at before the collision. So before the collision, I guess I would write it as R cross P. And let me just talk about the magnitude of the angular momentum. Hopefully you're seeing the direction. If I draw a line out here for R, maybe I will. So here is R out there. And then this is P, so this is phi, the angle between them. But an R cross P is into the board. Makes sense. When it hits it, it's going to make it rotate in a clockwise direction. So I don't think we need to worry about direction to solve this problem, but it's good to know that I could figure out the direction. The direction is a negative rotation. It's into the board here. Okay. And in this case, as I go to do my calculations like the other one, I would get an R, I would get an MV, I would get a sine of phi. But like I did with the other ones, why don't I put the R together with the sine phi? Because doesn't that make then this height, which we said was 4/3 A. So here is 4/3 A. So just like those other ones there, that is my initial angular momentum magnitude. Okay, so the bullet has that much before the collision. What is it after the collision? Well, after the collision, it is I omega, right? So here's what this is saying. This is saying that, and maybe I'll just leave it alone here for a second because there's a lot more work we have to do on this problem. But what it's saying here is if this bullet were to come racing in, this would be its angular speed right after the impact. Now, why do I say right after the impact? What about as it's tilting up? Does the angular momentum change as it goes upward? Is there an outside force as it goes upward? Yeah, we're back to that gravity, kind of the one you did. So again, whether there's a little bit of gravity, what I could need to really say here is the angular momentum right before impact equals right after impact. But if I have then an angular speed as it goes up, what happens to that angular speed? It decreases. Its angular momentum is decreasing, right? Because there is an external torque. There is the force of gravity. And so if I don't have enough speed, what I'll do is I'll get an angular speed, but it'll only go this far and then fall back down. So this angular speed needs to be enough to now lift it all the way up to that position. So maybe we should talk about that. What speed is that? And so here's where I'm going to deal with my conservation of energy. Now, the whole picture of conservation of energy may say this. That, okay, this is the total energy you have before the collision, 1/2 mv squared. Where does it go? Well, some of it, but not all of it, goes into a rotational kinetic energy. Is there any heat formed here? Yeah. And I would say probably quite a bit. We just did a bunch of problems that way. So I'm not even going to focus on that one for a moment. Let's talk about this now afterwards. 1/2 I omega squared. where does that energy go? So in other words, I'm going to apply conservation of energy again, but not from all the way from the beginning. I'm going to say, okay, the bullet comes in, it's got a lot of kinetic energy. A lot goes into heat. Okay, fine. But whatever's left has a rotational kinetic. Where does that go? Gravitational potential energy. Right. So then I'm going to put this as an mgy final. And I think that's the important key here. And if you want to write it as an inequality, I guess you can. What you need to be saying here is that that kinetic energy after the impact, the 1/2, excuse me, I omega squared, that has to be enough kinetic energy in order to give it enough gravitational to potential. If it has more than that, it goes all the way over the top. Great. But if it's just enough, then that's what we're looking for. We're looking for when it was just enough to get to that top here. Which is great because that's going to tell us what omega has to be, and then omega is going to tell us what the V has to be. Perfect. So we can use the conservation of energy here together with the conservation of angular momentum here to find out what is the minimum speed here. All right. Well, maybe I should go through a little bit more math here. I've got a 1/2 I omega squared, and I'm saying it has to be greater than or equal to capital M G. Now let me pause right there. Do you notice I just said capital M? Because what am I lifting up? Okay, I'm lifting up the block, right? And that's why I think the author earlier on said, don't worry about the little mass of the bullet. That and for another reason that's coming up. So I'm not going to worry about it. I'm not going to do it as a little m plus a capital, capital M plus a little m. Just capital M. We're lifting up the block. Okay, but what's the height I lifted? Good, and I hope you see the center of mass here, right? I'll draw the picture over here, kind of a cross-sectional view. This is what it looked like with the center of mass at a height A. I'm trying to make sure it will tilt high enough to get into that position, right? How high is that? Isn't it that? Isn't it this? So if this is A, isn't this root 2A? Right, the hypotenuse of an isosceles right triangle. So I'm trying to get it up to root 2 over A. So I start at A. I want it to go as high as root 2 over A. Now the reason I say that is because I didn't explicitly say in this problem, where do I want to call y equals to 0? But I really have. When I started this side and said all of my kinetic energy is rotation, what am I saying? Aren't I really saying my center of mass is at height 0? And so I've indirectly already said my center of mass is height 0. Yeah.
What if, for example, we did ignore the mass of the bullet and so the center of mass was shifted?
Right. So, okay. Then we would have to figure out where the new center of mass is. Now to do that, we would need to be told where did the bullet stop as it got embedded. Did it stop a little bit or a lot? You know, where did it? And so it would be a much harder problem. Could be done, certainly, but I think that's why the author just left it that and say, okay, look, this is going to be hard enough. Let's go from there. All right, so back to this. I hope you caught that indirectly I have really said y initial equals 0 at what you might call height A above that table. You know, that's really what I said in there. And I need to realize what I've done. That's why we did all these conservation of energy ones, right? You have that freedom to pick y equals to 0 anywhere you want. But once you choose it, you're stuck to it. Maybe I should have paused and asked you guys, where do you want to call y equal to 0? Because if you don't, you may include an initial gravitational potential energy. If you wanted to call the table 0, you would need to include an MGA for the initial height. But in either case, this one then becomes then what I would call a root 2 minus 1a. That is how much it has gone up. It's starting at a height of A, has gone up to a root 2. Now I'm not sure I want to keep writing root 2 minus 1 forever. So we'll be okay with you guys, since the square root of 2 is 1.41. Can I write this as 0.41 times A? And so we'll just take root 2, subtract 1, turn it into a decimal. And so here's what I have so far. I have 1/2 times I times omega squared must be greater than or equal to 0.41 mGA in order to lift it up. Okay? And so there's my conservation of energy. Like I said, taking us back to chapter 8. Do I have enough rotational kinetic energy to get it up? All right? That's what that is saying. And then I can put it together with this. Because if I put it together with this side over here, let's see what happens. So I'm going to take this and substitute it in. So this says 1/2 I. And in place of omega, I'm going to put a 4/3 MVA. 4/3 MVA. I'm going to divide it by I, and I'm going to square it and say that has to be greater than or equal to 0.414 capital M times G times A. Right? And so those are our two pieces putting together. It's, I think, what makes this chapter some hard ones to do. It's not a very long chapter in terms of angular momentum, but it is requiring you to go back and look at conservation of linear momentum and conservation of energy, and particularly those moments of inertia. Yeah?
I just have a quick question. Why the minus 1?
Why the minus 1?
Yeah.
Okay, so we start with a height of 1A. We finished with a height of 2A from the table. So if I call this y equals to 0, how high is that? It is root 2A minus A. So root 2 minus 1A. So how high up did it go? Like I said, maybe it would have been clearer if I had put here the initial energy is rotational plus gravitational. It all becomes gravitational. How's that? Calling the table 0. So it starts with some kinetic energy and has a height, and it goes up to just a height with no kinetic energy. But either way, then there's going to be a square root of 2 minus 1. All right, so good. I'm working along here. And it's looking really nice because aren't I going to have, when I'm all said and done somewhere, isn't there going to be like a V greater than or equal to something? And that's what the problem is. What is the minimum speed? What value of V do you need for this thing to flip over? Now we got a little bit of work to do. For example, when I square these things, I guess the 4 squared is a 16, but I'll take half of that to make an 8. Okay? So there's an 8. When I take the 3 and square it, that's a 9. The m squared, v squared, a squared is still here, so I'll leave that alone. The I squared, with that I, leave just one I, has to be greater than or equal to 0.41 capital M, G, and an A. And that's kind of nice that there's an A on both sides, so that'll go away. And so far, looking pretty good. Let me rearrange the math more. V squared has to be greater than or equal to, and so I'll move things to the other side. This would be a 9/8 and a 0.41 for my numbers. I've got a capital M and a G in the numerator here. Oh, I guess I got an I in the numerator. Okay, and so then there's the number. Then I got a little m squared and an a. Okay, looking better. I guess if I take the square root of all of this, I get what I'm really after. V has to be greater than or equal to. All right, so V has to be greater than or equal to square root. This might be a good time for my calculator. What is those numbers in front put together? What is 9 times 0.41 divided by 8? That's about a 0.46. So 0.46 for the number. There's a capital M, a G, an I, a little m squared, and an a. Now I wouldn't say I'm quite done, because I have things in capital M's and little m's and a's and g's that were given, but I wasn't given. So I'm sure they want me to write this in terms of what was given. So let's write I in terms of the stuff given. And maybe that's worth coming over here and then doing a calculation for a cube. Now this is the one I was talking about earlier that said, hey, the calculation of I for a cube can be a problem in of itself. I don't expect you to do that. I expect you to look it up in the table, although they don't quite have it in the table, so we're going to have to do a little bit of work here. But if we flip back to chapter 10, they do have a plate, a rectangular plate. So they give me this. Say, all right, let's see, how do they show it? Do they show a rectangular plate that has dimensions A, B, and is rotating around its center? Maybe I should do that. Rotating around its center. Okay? They say that the rotational inertia of its center of mass, and they write it as a 1/12. Hopefully it doesn't surprise you, because couldn't you think of this as a bunch of rods put together? I mean, if we were going to figure this out, a plate, we would take a bunch of rods and put them together. All right, so there's our 1/12. It's the total mass, and it's an a squared and then a b squared. Okay, so there is the rotational inertia of a plate. Now, we don't have quite a plate, but I'm hoping you'll see that if you add a bunch of plates together, don't you get then a three-dimensional solid object here? So what if you put another plate plus another plate? Terrible picture there. One plate plus another plate plus another plate plus another plate plus another plate, right? And I stack them. Isn't this sort of looking like a cube? And in fact, if we call A and B the same value, then, and we stack them A thick, I mean, isn't that a cube then? All right, here. So what I'm going to do is say, let's find out what is the moment of inertia around its center for a cube. Now what I would say, it's a stack then of these plates. Is that what he called it? Yeah, he does refer to it as a plate. And so it's a stack of plates. So I'm going to add a plate, a plate, a plate, a plate, a plate. Here's what's kind of nice about that. Look at the plates. This one you kind of have to figure on your own, but fortunately it's an easy one to do. If you think of this as the limits as capital M goes to 0 of the sum of a bunch of plates, now we can do what I've been trying to show you this semester. So I think this is what, the 4th time? Good. We can come up with our own equation, all on our own, right? From the calculus. I'm going to add them up. Now I guess I should have asked you guys, as I add them up, this is becoming a integral, and I should have erased that. What is going to 0?
The
Yeah, that's the thickness of the plate. I'm cutting them thinner and thinner. But in terms of the variables that are in here, is it A or is it B or is it M that's going to 0? It's the capital M. So it's capital M that's going to 0. So what I have is a dm, and then I have a 1/12, and I have an a squared plus b squared. I'm not letting the dimensions of the plate go to 0. I am letting the thickness of the plate go to 0. And what's nice about that is that as you add up a stack of these things, every stack has the same dimensions A and B, so you can pull them in front of the integral. And so we're down to a very easy integral, kind of like we did for the hoop. We just pulled everything out, and we had an integral of dm. So what does that integral of dm give me? Isn't that just the mass of all the plates, which eventually becomes the mass of the cube, right? And so let me kind of erase and continue on. So this then becomes the I of the center of mass of my cube then becomes 1/12 mass of cube a squared plus b squared. Or simply put, it is a plate that has thickness to it. You're going to get the same effect. And so instead of thinking of it as the mass of just a plate, it's the mass of the whole cube. Now the only other part I would probably put, actually 2 steps here. The first one is being, well, this was the general answer that had dimensions A, B. I erased the picture. Maybe I shouldn't have erased the picture. What is the dimensions of our cube? It's 2a. So let me put a 2a squared here and another 2a squared there to represent the dimensions of us. And what can be confusing then is we have an a up here twice. We have an a in this from chapter 10, which is the general dimensions of a plate, A. But we also had A listed for our cube. Our cube had sides of 2A. So that's why this A here becomes 2A, as well as this B becomes 2A. And that's kind of nice because when you take a 2 and you square it, it's a 4. So this is a 4. 4 plus 4 makes 8. And so this is 8/12 mass of the cube a squared. So that would be the moment of inertia of our cube. In fact, maybe I'll even reduce it a little bit. This is 2/3 divided by 4, yeah. Mass of cube a squared. Okay? Now I'm tempted to put it in here. Remember, this was the goal here. Come back to this equation and substitute it for I. But I'm still not done. What's the next step? Parallel axis theorem, right? This is the rotational inertia around its center of mass. Is that what's happening in this problem? No. So if you were having a rotate around this point, then I would be done. But it's not. It's moved over a little bit. So let me apply the parallel axis theorem before I finish this last step. And so now I need to find out what is the rotational inertia. So the rotational inertia of this cube about a corner is what I want. And so I know around its center is 2/3 ma squared. That's what I just figured out. But now I have to move it, so it's m, by a distance of the square root of 2a squared. So 2/3 ma squared plus 2ma squared, which I guess is a common denominator of 3. Whoops, 3. Common denominator of 3. And let's see, to get this to a 3, I got to multiply by 3. So that's an 8/3. So I have an 8/3 ma squared. Yay! Okay, now I can finish the problem. So you need to come back and think about the moment of inertia of my cube. But now that I have it, then I can put in that the velocity has to be greater than or equal to the square root of 0.46 k capital mg over little m squared a, and then I is 8/3 capital M a squared. And it looks like I can then put some numbers together there and kind of rewrite that. But in the interest of time, let me not and just say, okay, that's it. All right? Wasn't that an easy problem? Right? Just conservation of energy, conservation of angular momentum, fill in the details. 2 hours later, you'll be done. Okay? And so, again, it's probably worth saying, but I think you've learned it by now. Physics is about knowing how to apply a few powerful fundamental concepts to explain a universe of phenomena. Right? It's the reason it's there on the syllabus. There's not that many principles of you learning. But the deductive reasoning, the problem solving, the details, keeping track of them, working them out, knowing where to go in the next step is the hard stuff. Well, so far we've been doing a lot of problems that do have conservation of angular momentum. Let me do 2 more, as you'll see, that do not have conservation of angular momentum. They do have an outside influence. They do have a torque acting on them. And so what would we do there? And the 2 are number 58 and actually 59 because they go together. Number 58 is the starting one, but you'll see 59 is a continuation. So I kind of think of this as one just really long problem. They both have a part A and a part B, so it's really like one long problem, part A, B, C, and D. Let me read 58 here. 58 says this: a uniform solid disk is set into rotation with an angular speed omega about an axis through its center. While still rotating at this speed, the disk is placed into contact with a horizontal surface and released as shown in the figure. A. What is the angular speed of the disk once pure rolling takes place? B. Find the fractional loss of kinetic energy from the moment the disk is released until pure rolling occurs. Well, I was concerned that maybe you wouldn't get a good physical picture of this, so I brought it out. Let me move the table here out of the way. But here's what they're saying. Take a wheel. Now, the description of the problem is a little different than this one. They say a solid disk, and this isn't solid. This has spokes. But imagine it being solid, and it says start it spinning. Initial speed, omega. Omega I. Set it down and let it go. What's going to happen? Pure rolling will take place. Just wanted to catch it. Last one I broke the axle. It hit and fell over and the handle bent, and I didn't want that to happen. All right? So, see it again here, right? There's omega. Okay? You set it down. There should be some friction here. And then now, pure rolling should take place. So that's the question. What's the new? And I forget, did it say angular speed or rotational speed? 58. What does it say here? A. What is the angular speed once pure rolling takes place? So do you see the beginning part? Do you see that as it's spinning, it's going to be having some friction like this? That friction is going to do what? Going to be doing 2 things, right? As that friction is there, it is pushing the wheel this way. So this will start gaining a horizontal speed, a translational speed. What else will take place? Yeah, this friction is providing a torque, which is slowing down the angular speed. And that's what this problem is, figuring out those 2. So we've got the 2 things going on at the same time here. So maybe I'll divide it into the 2 halves. I've got the linear motion here, or the translational motion to think about, but I also have the rotational motion to think about. The free body diagram is over here. Free body diagram. Here is this disk. And of course, it is being pushed down by the force of gravity, mg. You would even say it's being pushed up by the contact normal force. Each of those are kind of irrelevant for what we're going to discuss. I don't want to forget them. But does the object move up or down? No. So the force of gravity pushing it down is equal to the normal force pushing it up. Okay, fair enough. Do any of those forces give it a torque? No. The one that's relevant here is as this one is rotating, it puts a force on the table this way, so the table puts a force that way. And so there is my kinetic friction. Why kinetic? Why not static? Yeah, there's slipping going on. It doesn't become static until when? Yeah, the word we use is pure rolling. No more slipping going on. And that's the question. How much angular speed does it have once pure rolling begins to take place? What is the angular speed of the disk once pure rolling takes place? And then B, find the fractional loss of kinetic energy from the moment the disk is released until pure rolling occurs. Okay? So as I look at this diagram, I would begin to say, is there an external force making it change its linear momentum? Oh, definitely, right? Isn't that what the friction is? That's what's giving it its speed. But I would also say that that same frictional force here, if we calculate the torque around the center point, is then a torque, and so we are losing an angular momentum. So we're gaining a translational momentum, but we're losing an angular momentum. So nowhere up here am I going to say the initial momentum, whether linear or rotational, is equal to the final. It just, that doesn't happen. And so I'm back to my Newton's second law of motion, and I would stand over here and say, well, when it comes to the linear motion, I would say the acceleration is equal to the force of friction divided by the mass of the object. Whereas over here, I would say the angular acceleration is equal to the torque divided by its rotational inertia. And so there's my problem. It's a kinematics type of problem here, or maybe it's more of a, you might call it dynamics type of problem. But what I have is I have Newton's second law here. Let's apply the same ideas to each of the two situations. But they're happening at the same time here. Let me work this one out a little bit more. What would the torque be? Yeah, so maybe I should call this a capital R or something for the radius of this disk. What would the torque be? Force of friction times R. And if you want me to put, I'll put sine of 90 degrees so that you don't forget, or that you know that I know that there's got to be an angle between them. But this angle right here, there's R, there's F, it's 90 degrees. So there's the torque. What's the rotational inertia then of a solid disk? Good, 1/2 mr squared. So this simplifies a little bit to force of kinetic friction. One of the r's cancels off. I guess the 2 goes upstairs. So the, see if I did that right. Yeah, the 2. So that's everything upstairs, and then I have an mr. Okay? So that would be a way of writing the acceleration. Let's write the velocity. Let's talk about the linear velocity. What would you write for the linear velocity? Well, maybe I should ask, is this a constant acceleration problem? Which really comes down, is this a constant force problem? Yeah, and it really is. I was glad they gave me an easy one, because it may not feel like an easy one here. But it really is. And this is what we did in Chapter 5. Didn't we say that if two things were sliding, the amount of kinetic friction is pretty much a constant, regardless of how much sliding goes on? So at first, I would say there's a lot of sliding going on. A little bit later, now that it's kind of moving along, there would still be sliding going on. But doesn't that give you the same amount of frictional force? And so that was our whole solid to solid friction, the easy friction of chapter 5, right? So this is a constant frictional force, at least until pure rolling takes place, which is what we're after. So during this problem, where we have kinetic friction, it is the same amount of kinetic friction, and hence the same acceleration. And hence I can use those kinematic equations that the one I'm thinking about is kinematic equation number 1, which looks like that, right? The velocity equals initial velocity and acceleration times time. So if I put in my numbers, I would put a 0 plus, and maybe I should pause there, 0, right? Initial velocity is 0. Initial translational velocity is 0, right? And then my acceleration would be the force of friction divided by mass multiplied by time, and that would be my final speed. So looking at the linear motion, I'd have final speed is force of friction multiplied by time divided by mass. If I do that same thing over here for the rotation, I guess I would have final rotational speed is equal to initial rotational speed plus alpha t. Now in this case, the initial rotational speed is not 0. The angular acceleration is what I just worked out. I left the middle in between because I'm going to put a minus sign here. Why? Right. I mean, you can pick the sign that you want, but I will say this. If we are going to pick an initial speed as positive, the torque is then the opposite of the positive. It is in the negative direction. We could have easily just picked that negative and that be positive. But the point is, these two terms got to be opposite in sign because it is a slowing down here. Okay? And so that's why I'm going to pick the negative here. Well, good. It's looking good so far because that really is the problem right here. What is the final speed? Well, this is kind of nice. It doesn't say how much time it takes, right? But couldn't I solve this for time and put it over there? Let's give it a shot. All right. So if I go m times v divided by the force of friction, that would tell me the time. So that's how much time it would take before my, to get to that speed. And if I put that over to here, then I would have initial speed minus 2 force of friction over mr. And then I can replace t with an mv over force of friction. That's kind of nice because force of friction cancels off and mass cancels off. And so now this becomes initial speed minus, and what do I have here? A 2. And then I have a v over an r. Well, this is kind of the last part of step 1 here. Do you see this? What's v over r? Right, and that's the key to pure rolling. Remember they said when pure rolling takes place. So when pure rolling takes place, it looks something like this. When pure rolling takes place, the movement of its center is the same as its rim. The speed here of the rim is easily calculated in terms of its angular speed. That was the chapter 10, the relationship between its angular speed. And so when it is slipping, there really is no connection between its angular speed and the speed on the ground. But when it is pure rolling, then the speed of the rim is the same as the speed on the ground. And hence, we can then say the speed of the rim, which looks maybe something like this, if you remember, that the translational speed was equal to omega times r. As far as the radius of the rim, that's the connection. So v divided by r is really omega. But what I want you to see is which omega. Isn't it final omega? Right? And so that V over R would be the final angular speed. Now if I move that to this side of the equation, that makes 3 times the final speed is equal to the initial speed. Or, as they asked it, what is the final speed? The final angular speed is 1/3 of the initial speed. Ta-da! Hey, that was easy. Right? And so that's my new angular speed. 1/3 of what I started with. And I have outside forces. In this case I have outside force, which changes its speed, and I have an outside torque, which changes its angular speed. So linear speed changed, angular speed changed. And so that's A. B. B says, and I think we've done most of the work already now for the rest of this, but B goes on to say, all right, now, what fractional loss of the kinetic energy from the moment the disk is released until pure rolling occurs? Okay, so obviously there was rubbing going on. That rubbing is forming the heat. It's also the part that gives us the friction that makes it go. But it's really a conservation of energy question. It's this. It is saying, all right, the initial energy is equal to the final energy, right? So what energy did you start with? Well, it was rolling in your hand. So I would say it started with that much initial energy. Once pure rolling took place, then it had a translational energy and a rotational energy, and then of course some heat that was created in the process. And what are they asking for? Well, they're asking for how much heat was formed in comparison to what it started. Maybe I better read it again. It's like those other problems. Find the fractional loss of kinetic energy from the moment the disk is released until pure rolling takes place. So they're after this, Q over the initial energy. So putting these two ideas together, here's the initial energy, 1/2 I omega I squared. This then would come out to be 1/2 I initial I squared minus 1/2 mv squared. I should say final squared. There is no initial, so 1 minus 1/2 IV final squared. Right. And as I work through the math here, this would then become a 1 minus, and then I guess I have an mv final squared over, so when I look at this, an I over an omega I initial squared. Then this becomes a minus, and I guess this is just final speed squared over initial speed squared as I break them down into its 3 fractions. The I cancels off there. Okay? And so as I work this out, this is 1 minus, well, I'm going to leave the m upstairs. Final speed, as we already mentioned, somewhere over here. Did I erase it? But the final linear speed must be equal to the final angular speed times r. So I'm going to write this then as an r squared omega final squared. And likewise downstairs I'm going to write as a 1/2 mr squared, because that's the rotational inertia of this disk. And initial speed in terms of final speed is 3 times the final speed squared, right? That's what we just worked out over here, that 3 times the final speed is the initial speed. This one's a little bit easier. This is final over initial. So final over initial is 1/3. So this is 1/3 squared. All right, so it's 1 minus, let's see, it looks like the r squareds cancel, good. The m's cancel, good. The omega squared cancels, good. And it looks like I'm left in the upstairs with a 2 from here and a 9 there. So that's 2/9 minus 1/9. which is 1 minus 3/9, which is 1 minus 1/3, which is then, yay, 2/3. Aha, wasn't that easy? So 2/3 of the energy is lost into heat during this process. So that means 1/3, I guess, is left for the other two forms of energy. 59 continues on. It says, now, suppose this solid disk of radius r, given an initial spin of omega I, about a fixed axis through its center, is then lowered carefully into a horizontal surface and released as shown in the last problem. Furthermore, let's assume that the coefficient of friction between the disk and the surface is mu. A, what is the time interval that occurs? What is the time interval before pure rolling occurs? And B, what is the distance that the disk travels before pure rolling occurs? So the last two parts here, the first one is how much time is it going to take? Well, I guess that's what this one is all about. This is this T for time. Let's see, maybe I should move down to here. But how much time is it going to take? They go ahead and use the coefficient of friction. Let's see, do they have that in their, I think they want that then in their answer. And they even say make it look like this, so they tell you how to look at it. But we've already done time is right there, so I'll call this part C, and so time equals, what did we have over there, mv, and that's really the final v, divided by the force of friction. Well, let me start with the force of friction. Force of friction takes us back to chapter 5, right? This force of friction is the coefficient of friction times the normal force. I didn't work out the free body diagram, and maybe in the interest of time I won't, but can you see how the normal force is equal to mg here? All right, so this would be coefficient of friction times mg, so the m's go away. And then the final speed would actually be, I guess, r times omega final speed. And final speed, as we just said, is 1/3 of the initial speed. And so the radius times the initial speed divided by 3 mu g should be the amount of time it would take before this pure rolling occurs, which I think it agrees with what they say. Show that the time is r omega naught divided by 3 mu g. Sure. And so how much time does it take? And the last part of this then is how much distance did it travel? And again, we can do these in different ways. Maybe I should go final speed squared is initial speed squared plus 2a, and then distance traveled. So distance traveled is the final speed squared minus initial speed squared divided by 2a. So in this case, it's final speed squared over the 2a. Now the 2a is force of friction divided by its mass. Final speed squared is r squared times final omega c squared. I'll put the m upstairs, and then this is a 2, and then the force of friction is the mu mg, and so the m's go away. And then, of course, final speed squared is 1/3 of the initial angular speed, and so 2 mu g. And so when I do that, the 1/3 squared is a 9 with the 2 make an 18. So I got an 18 downstairs. I got an r squared. I got initial speed squared up here, and I guess I got a mu and a g. And so hopefully that also looks like what they're saying here, that it should be an r squared and omega squared in the numerator, an 18 and a mu and a g downstairs. Good. And so we've got a more complicated problem. You can see why it's magenta in color, but one that hopefully is not too overwhelming. Does that make sense? Did a lot of good problems? Didn't quite mean to take that time. I wanted to do a little bit of 12, but I think that was probably better. just a few minutes early. We'll stop early as long as you guys promise not to let the word out that this is an easy class, that you get out early, that it's because there's just going to be too many people signing up next semester. So don't want those rumors out there that an easy class, GPA raiser,